For light?
Yeah.
I don't know.
Green.
Doesn't look like it. Oh, there we go. Conservation of lights or?
Lights out. Let me make a couple announcements. First of all, we'll have a group photo taken after the first talk, just on the stairs, outside the main gate. Second announcements is there will be a game after last talk. And okay, the four half the speakers have agreed to participate. So I don't know how many you would like to participate, but no matter what the skills are.
It's not going to be speakers versus audience.
Well, we could try that, okay? See how many audience will participate. Lastly, there will be a banquet at 6 of the Graduate Hotel.
You will not be in the graduate hotel, that's at the campus club.
Oh, the campus club actually just, okay, change the plan. It's just across the street, Washington Avenue. This is, yeah, it's very close. It's even closer, yeah. California Union. You can go to the banquet whether you played or not. With all these announcements.
But not if you commit, even if I'll.
Huh?
Not if you commit.
Yeah, right. Actually, I will alert you, there will be referee for the game. Okay? So just, you can play, you don't play too recklessly. 2 yellow cards when you are out for the game and the banquet. Okay, with all these announcements that I'm happy to have Mohammed Abouzaid to come back to the Yamabi Symposium to start the program today. And here's his talk title for homotopy and the bordism theory.
Thank you.
Okay.
Thank you very much. It's a pleasure to be back here. So I was just thinking, actually, the first time I'm here was just over 20 years ago. In spring 2004, I was a second year graduate student, and Sasha invited Abouzaid to give a lecture series here, and I looked at I somehow saw an announcement, and the title was what Paul Seidel gave me to work on as a thesis problem. So I came here, and what Maxime did, and he gave a lecture series. The first lecture is basically explained that he solved everything I was planning to work on for my thesis. But it turned out things were okay. So afterwards, I went out with them for lunch, and then we went to Sasha's office for more discussion. And that's how I started getting involved with mirror symmetry. So I have very pleasant memories of this place. So today I will talk about some joint work with Andrew Blumberg on a rather different subject, even though the back of my mind there's still some goals to think about to relate this to mirror symmetry. It's a very large scale project. The first part of it is up on the archive. That's what I put the reference there. If you are interested in more propaganda about it, this talk will basically be propaganda. There was a lecture series at MSRI 2 years ago, I think, maybe. Time flies, and I write very slowly. Yeah, so what is this about? So this is about some question that basically goes back to Floer, which is Morse theory allows you to extract a homology group out of a Morse function and to relate this homology group to ordinary homology. And the question is, can we do Morse theory for generalized homology? Okay, and Floer's motivation, evidently enough, you can see this. This is actually in his first paper, one of his first papers on what then became Floer theory. I think this is the one on Witten's action functional or something like that. It has Witten in the title. So his motivation is that if you just ask this question about Morse theory and finite dimensional manifolds, it's kind of hard to find an application because Morse theory, ordinary homology, and so on and so forth. But for this action functional that he introduced and that many of us study here, there is no classical topology analog. And so if you can do Morse theory for generalized homology, then you really will produce a new invariant. And then you can try to use it for various geometric purposes. Okay? So just for those who are not familiar with the subject, so what is Morse theory about? So let's say M is some smooth Riemannian manifold. Are function with non-degenerate critical points. So points. Now, what that means basically is that when we teach calculus, we tell students about the first derivative test, looking for critical points, and we teach them about the second derivative test, telling them about finding minima and maxima. And this non-degeneracy basically means you can apply the second derivative test, you get something meaningful, as opposed to this kind of we cannot tell because the second derivative also vanishes. So that's and now out of this, what you do in Morse theory is you can construct a chain complex. Which is generated by the critical points. And the fundamental thing is that it is constructed out of the space of gradient trajectories of a function f. And I tend to go down gradient slope, but anyway. So this is some critical point x, and this is some critical point z, and of course there's going to be some gradient flow lines that go from x to z. So implicitly in there is some transversality assumption that you put in. That's this more small assumption that Chris pointed out. And you look at this moduli, okay? Look at the space of all gradient trajectories that goes from x, that start at x and go to z. So let's say this is d gamma I dt minus I gradient. Okay. So in usual Morse theory, you basically only look at the spaces of gradient trajectories, which have so that when you take one of them and you deform it, the space is either 0 or 1-dimensional. Why is that? Well, because if the space is 1-dimensional, then generically you'll go with one parameter family of gradient trajectories, and at some point it may break. But we're really not looking at trajectories, we're looking at possibly some compactification of the space of trajectories, where, again, in the limit, you allow yourself to, instead of one thing going straight from x to z, you stop at y. And the fundamental result that is proved, and the first thing that you prove in the subject, is that the moduli spaces, call them M bar X, B are manifolds with corners, I mean, technically making sure that these are really manifold components is very tricky, but if you're only looking at 0 and 1 dimensional things, it's not so hard. 0 dimensional things, very easy to check it's manifold, there's no corners. But 1 dimensional things are intervals, and not like not so difficult. Okay, corners. And the facets of this manifold with corners are exactly given by concatenation maps. Something that takes a gradient trajectory from x to y and a gradient trajectory from y to z to a broken gradient trajectory from x to z. X to z. Okay, this factors through the boundary. And not only that, this inclusion is the inclusion of the codimension 1 stratum. Codimension 1. Let me just say facet. Okay, and all such facets are labeled uniquely by such a critical. Just to make sure we are on the same page, what that means, so it's quite easy to say what it means. Like in this picture, this moduli space is 1 dimensional, it means it has boundary, and the boundary is labeled by critical. Of course, here I drew some, an interval in this boundary. The interval goes from 1, but there could be somewhere else in the back of this Riemann surface, for example. There could be another gradient trajectory that goes from x to z, and it breaks somewhere else. So there could be this does not need to be connected. So what I mean by we should be on the same page is G has dimension 2, then no, it could be very complicated. Maybe here there's some Venus. No? Okay. But I drew some corners. Okay, and every one of these is labeled by some Lagrange. By some critical. Yeah, autofill. So anyway, and then this corner here, okay, so these maps satisfy some associative property, and so that this corner you can actually tell that this is the image of MR X Y1 MR Y1 Y2 to Z going to MR X. So here I said something about the facets are of this type, they're labeled by other critical points. And once you know that, and you also, if you have this and you also have associativity, then you also know that every higher codimension 1 stratum is labeled now by a sequence of critical. Yes.
Codimension 1, dimension 0.
I mean codimension 1 in the whole thing, but yes, codimension 0 in the boundary. Or maybe that one.
Yeah.
Okay, good. So this is the structure. And now, as I said earlier, from those, if we just forget everything about dimension 2 or higher, and remember only dimension 0 and 1, then we get a chain complex. In fact, more precisely, if we remember only dimension 0, we get some operator on this module generated by the critical point. And if we remember dimension 1, then we can know how to prove that d squared equals 0. Okay, and that's all. That's all you use. And Floer very early on suggested that we should use all the higher dimensional modulus. Okay, proposal. All. So how to go about that? Well, so the first solution to this problem is given by Cohen and Siegel. 93, 94, 3. And they did two things. One thing they did, which is very, as we, kind of later in the talk will be kind of some kind of fundamental, we will reinterpret in a fundamental way, is to formulate this structure abstractly. Formulate structure arising from Morse theory abstractly. And this is the notion as a flow category. And I'll come back to this. And two, they did is that they used very elaborate, combinatorial, well, anyway, elaborate generalization of the Pontryagin-Thom construction. The Pontryagin-Thom construction is the construction that relates some kind of theory of bordism to some kind of homotopy groups of Grassmannians or spheres or something like that. To extract what I will call here, well, let me use their language, a spectrum. Okay, and more precisely, they extracted stable homotopy type, but okay, from and there's some technicalities that I'm omitting here, and we'll get to them as we get. So, goal of somehow this program with Blumberg is to not do this. Okay, and that's basically because this is by far the most technical part of the work, and it forces you, if you are somebody who is doing Floer theory or some related theory, it forces you to kind of produce all this geometric input and then essentially feed it in some large machine, which you may or may not understand the workings of, but regardless, that you can a lot of difficulty controlling what comes out of it. Okay? And so the goal is to this program is describing is to do everything as geometrically as possible for as long as possible. And that requires taking this notion of the flow category even more seriously than Cohen, Jones, and Siegel. Okay? So, what is a flow category? Well, as I said, flow category is what I just described here. So a flow category is collection of objects set of morphisms, but my morphisms will be smooth manifolds with corners. And Y, corner. And then 3 associative composition maps. Just like in here. And then the fundamental property is that key additional condition is that the images of the composition maps are inclusions of codimension 1 boundary strata, and all such codimension 1 boundary strata arise in this nature. And I forgot here to say compact. Boundary strata codimension one boundary is given by composition. So in some sense, I've already told you what it is. It's what you get out of first. Now, here, the only thing I said is compact manifold. Okay? So you can decorate this any way you want. You can add oriented. Okay. Now, technically, if you add oriented, then there is some small annoyance you have to deal with, which is you have to kind of choose some parity for every object. So basically, you have to choose what in Morse theory is the Morse index. You have to remember something like the Morse index. Okay, but I will just omit that. There's some additional choice that goes here. Okay. And when you do so these are compact manifold, you just add oriented. Okay. And then you continue, and then you have to say, oh, these codimension one boundaries. They have to respect some orientation. Okay. You can do stably complex. More or less the same thing. Remember some parity. Maybe you want to do better than some parity, but that means the same vector space. That you know what has odd dimension, what has even dimension. Okay, then here you impose that they're stably complex, and here you say that the dimension one boundary structure is stably complex. And then there is, you can go even more. You can put, I don't know if you pull it here, stably framed. The stably framed means the tangent space, instead of being trivial, it becomes trivial when you add to it trivial vector space. And then again, here you have to pick a vector space for every object. Here we put the stably framed. Okay. So now, this is the story when you do Morse theory. You can actually do something even more crazy, which is what's relevant for Floer theory, which is you can drop this word manifold, and you can replace orbifold. And that's because when we study moduli spaces of pseudo-holomorphic curves, we know that we generally have some problem where we cannot achieve transversality because of the presence of symmetries. Okay, and so we don't expect to get a manifold back. But in fact, in practice, unless you are working in very special situations like, holomorphic curves in CPN or Grassmannian, you don't even get orbifold. You have to have something, some notion that's more general, which maybe these days we're just going to call. Today I want to call it Cornish. Why not? Normally I've been calling it the right one. Okay, and so there's, you replace manifolds, well, Cornish phase orbitals, you can also have boundary, you can also have corners. Everything I say here makes sense. And then you can combine what's happening here with what's happening. You can talk about stably complex orbifold or stably framed Cornish space, and all such possibilities are allowed. Okay, but I just, that things will become very complicated if I introduce all these things. If you look at this paper on the archive, okay, what you will see is that we focus on this case and this case. We focus on stably complex derived orbifolds or stably complex coordination spaces, and we also discuss the case of stably framed manifolds because I will say second, that's some kind of fundamental. Any questions?
You need this like compact manifold corner, that there's the corner structures and you can escalate.
You can surely finesse it away. We, however, managed to figure out in some separate work with Mark McLean and Ivan Smith, we basically figured out a way to just solve the problem that's been giving us a headache for 20 years. We don't have, I think it's not a problem anymore. But not by doing analysis, by appealing to something called smoothing theory. Anyway, there's some way of just getting the corners, but essentially go through. Yeah. Okay. Great. So now, so this is the structure we encounter in Morse theory, in Floer theory. Now the question is how to extract this spectrum from it. Okay. So here are two incorrect ways of thinking about spectrum. One. First way of thinking about the spectrum is that it is a topological space. Equipped with commutative and associative group law. Okay. So you have the topological space X, there's a map, addition, X plus X, there's a unit, addition is associative, addition is commutative. Okay. If you have such a thing, you have a spectrum. That's actually true. Okay. The problem is that most spectra don't have something like this. What they have is this structure up to some higher coherences. Like up to homotopy, but then the homotopy itself has homotopy. Okay, so if you're not an expert, you should just ignore all that and just think this. Okay, it's an incorrect way, but it's essentially morally the right thing, what we're looking for. Two, a homology theory. E, some functor that takes the topological space to graded abelian groups. This functor, just like everything we ever study in homology, should be homotopy invariant. And it should satisfy Meyer-Wertz. Cover. So there's a little bit more. You have to have some kind of connecting. You also have some kind of connecting homomorphism for cover, and then that connecting homomorphism. That connecting homomorphism allows you to build a long exact sequence on homology groups whenever you have a good enough cover. Okay, so this is again every spectrum gives you such a data. It turns out that the homology theory does not quite determine the spectrum because of some very annoying issues having to do with what happens when your topological spaces have infinite homotopy type. Okay, for finite dimensional CW complexes, this is perfect. So these are two. This is how I think one should think about spectra. Okay, and one should just not, as I said, one should not worry about the fact that it's not correct. Because so
Give us an example of a spectrum.
well, I will extract something. Give me 30 seconds, and then I think I will say something, and then you won't worry about that point anymore. Okay, if you either of these things will determine a graded abelian group. Which in this first case is just the homotopy groups of this space. And in the second case is the value of the homology theory when evaluated at a point. Okay. And so what I want to explain next is how to produce this graded abelian group. Okay, and then what I will say is, then indicate how this graded abelian group out of flow category, but first I will explain how to do it. Yeah, I got a flow category. And then once you have that, then I will say, well, actually, we could have enhanced this to a topological space, which would then answer y'all's question. Or it will, we could actually enhance this to a homology theory, okay? But I don't want to give a spectrum because it just, but and then I will tell you what spectrum I'm thinking. Okay, so what is the homology? How do you produce this graded abelian group? Let's go back to the initial motivation of Morse theory, okay? If the bar is the low category associated to a Morse function on M. Okay. Whatever this is should be something familiar. This should be. Well, now I want to say the value of my generalized homology theory on this manifold. Okay. But now to give away the title, this should be the bordism theory. Bordism groups of N. Quick reminder, what is bordism is. So all if X is any topological space, then we can produce a graded abelian group and let's call the graded abelian group K. This is the grading of X, which is generated by closed manifolds mapping to X modulo the relation that if you have, and well, there's one way to do it. Let me do it like this. If I have W over X, where W is boundary, then class of the boundary W is 6. Okay. So some people may have seen already just bordism groups of abstract bordism groups. That's the case where X is a point and there is no map to remember. And you just say, you look at all closed manifolds. Okay, this should be compact. You look at all closed manifolds, modulo the bordism relation, which says that after the boundary of something, you set them equal to. What is K there? Thank you. The dimension of N. This is a definition. It doesn't require for this target to be a manifold. We can define it for any topologicals. So one of the fairly basic things you can prove once you have learned Sard's theorem, I think should be enough, is that this forms a homology theory. Okay. The hardest thing, of course, the hardest thing to prove is transversality. And you make your life a little bit easy if you pick nice enough covers. What you do is you take your manifold mapping to some target, and you assume that the decomposition is somehow by things which have nice boundary. You take the inverse image of the boundary and you break it up into pieces. Anyway, it's not too difficult, and I strongly suggest the book of Conrad and Floer, Periodic Differential Maps. As a reference for this subject for people who have never seen it. It's really quite a pleasure to read, and you can just ignore everything in it but periodic differential maps. It's just the first half of the book is just the construction of bordism theory, which really would be accessible to any student who has taken a differential topology class. Okay. And that's what we should be trying to recover. Okay? But now, we're not gonna do it for any x, we're doing it for manifold, but with a more structure. Target. And is a manifold with Morse function. What we want is an invariant of this flow category, n bar, and we should call it n bar s. Recovered. Bordism. That's all. And well, we know how to do it for ordinary homology. And in fact, you know, Witten actually did it for Durand cohomology, interestingly enough, instead of really thinking about singular cohomology. And you basically use more or less the same language. Okay, so now take n nothing m transverse to the gradient. That's not well defined, but in transverse to the gradient flow, i.e. to the descending manifold of the critical points. So it's a standard thing. In Morse theory to say, oh, well, you know, I have some critical point here. I can look at some open manifold. In fact, it's a ball, which is just all the points which, if I were to flow back up along the gradient flow, would converge to my critical point. And I, despite almost 20 years of thinking about Morse theory, can never remember which one these are. Today we'll call them the unstable manifold of X. It might be the stable manifold of X. Okay, so now there's something that happens in that's kind of again in the way that Floer theory makes you think about Morse theory, that suggests that these, which are open manifolds, are in fact naturally the interiors of closed manifold with coils. How do you think about it? How do I think about it? I think about it as something like this is like a gradient flow line, but not infinite, but which is semi-infinite. So this is a gradient flow line. Gradient flow line, which is parametrized with domain minus infinity to 0. Okay, so minus infinity is going to the critical point. 0 goes to some point in the space, like here. So those two. This you can evaluate. But Floer theory says if you're in a situation like this, you're thinking about flow lines, you should naturally compactify it by broken flow lines. Instead, some situation with X, something that goes to Y. This is infinite copy of R, and then let me do another one to Z, another infinite gradient flow line, and finally a finite, and I'm just going to maybe do this to make it a finite grow line. So this is R, this is R, this is minus infinity to 0. Okay, it should be pretty clear how you would glue such a thing together. The picture you should have in mind is that there's a big copy of R here, a big copy of R here, and a finite copy here. And if I choose in the usual way, Morse theory, in Morse and blur theory, I can cut this region and then I glue this to this. Glue the boundary to the boundary, I can cut this region and then glue to the boundary to the boundary, and finally I have, again, a semi-infinite. So that's how you formally make, implement the idea of making a manifold N mapping to M transverse to the gradient flow. You say, I would like it to be transverse to every single one of these compactified spaces of descending limit. Okay? Well, you've done that. You can do is define a new object that is assigned to N. This car is not supposed to work in black one. And then you assign to N and X, which is a critical point of F, the fiber product. And we call it curly N of X equals N crossed into M with W bar unstable of. So the picture that I have in mind is element of the space is an element, a point in N, and a point in N and a gradient trajectory the other way from its image in M back up to X. And maps somewhere. I take a point here that maps there, and then I flow back up. So down that way. This is the okay. And of course, implicitly, we're assuming that everything's true. So I'm just going to ask you to take on faith that this is a good object to consider. This is a manifold with coordinates. I mean, that you can take it on faith. I basically told you everything why it should be a manifold. That's what it means for them to be transversed. If I take the fiber product of a closed manifold and a manifold with corners, over some evaluation map to some good manifold, I get something with corners. What does it satisfy? How can I relate these manifolds with corners for different critical points X and Y? Well, to do that, I just have to understand this part, because this has no boundary, this is closed. Okay? Now there's a key equation which says, I've already basically indicated to you up there, which is that there is a map, okay, W bar unstable X cross bar Y to W bar unstable. Oh, I'm sorry, it goes the other way. This is the map that just says, oh, I'm going to take a gradient trajectory from X to Y. And I'm going to take one of these half infinite things from Y to somewhere, and I just concatenate. Exactly the same thing as when we did. And exactly as the same thing as what happened when we did the Morse gradient flow line. This enumerates all codimension one strata or rise from this construction uniquely or labeled. Why? By such a group. Okay. So this construction that I wrote over here inherits it. So what I mean by that is, similarly, we have maps N bar X Y cross N of Y to N X, which give all that. Now, what I have given, just like before, I said, you look at it with a flow category, or you look at a Morse theory, you see what it gives you on the moduli spaces, you formulate it abstractly, you get a definition of a flow category. You take this notion, you get, this is the definition of a flow module. Going into new definition. Now to define bordism, it wasn't enough to just look at closed manifold. We have to look at closed manifold up to boundaries. But you now do exactly the same thing. So repeating the process. For W over M. And this has this manifold boundary. Oh, I made a mistake. Board work. Anyway, repeating that process gives us a definition of what it means for a flow module. Gives the notion of null bordant flow module. Okay. Now notice, by the time we're talking about this n of x, and when I say, it gives the definition of a flow module, this notion doesn't know about the manifold M anymore. Okay? It just says, I have a collection of manifolds with quarters, one for every object of the flow category, and they satisfy this equation. It doesn't refer to the manifold, to the target. And this bordism, again, is the same thing. You have now a collection, let's say W of X for every critical point, and their boundaries are basically these things plus n. So there's no. So now, theorem says that the bordism groups of X M, sorry, are isomorphic. The bordism groups. And I just erased it, it was here. You can go here and you can decorate as much as you want. All there in. Okay. So in the last 10 minutes, I want to give some indication. So now that I've defined the bordism group, I want to fill in. Oh, it's gone. It's here. I want to fill in what is missing, which is like, okay, but it's supposed to have more stuff. There is the space. Slash homology. Yes.
I'm wondering, how does this depend on the Morse function I?
Well, so this actually says it's invariant because it's given by the bordism groups of M, right? But of course, you can prove that independent. You can prove that independently. If you have two different Morse functions, there's going to be a continuation map, and then you can use that continuation map to relate these two bordism groups and show you the right side. Any other questions? Yeah.
Yeah, I mean, like in witness definition, you can actually use it as a computational tool instead of such here.
I mean, of course, I don't know what, but you can use it to filter, you get something about, filtering and some of that. But the reason that in finite dimensional setting, I find it very hard to use. Of course, the answer is yes. Of course, you are right. Like if you have some, my thought is like, yes, but you could just take a CW decomposition. Okay, but of course, why was this situation useful as a computational tool? Because you have these big spaces where it's much easier to write down a nice Morse function where like it's even or something like that than it is to write in CW decomposition, right? So the answer is yes, you can do it like that. It's more difficult because, now being supported in even degrees does not determine the answer because there's this spectral sequence and your differentials all over the place. So, but you can use it as a computational tool, sure, yes. Okay, where's the space? So I said that, we took a single manifold and we produced some flow module out of it, and then we took the bordism groups of all flow modules, and that was our invariant. But it turns out that you can look at the space of all flow modules. So what kind of space is this? It's some kind, the best way to think about it is some kind of combinatorial object, some kind of simplicial complex. So it's going to have vertices, what I said earlier, and edges, some kind of, one parametric cobordisms of flow module. And then faces, something like this. I give you a flow module here. I'm going to give you a flow module here. We call it curly n0, curly n1, and curly n2. Okay, and then I give you some cobordism, n01, and n12, and n02, and I'm going to give you some n012, the cobordism of cobordisms. Okay, so that is actually the topological space that you should be interested in. And now I want to point out, I said you should think of spectra as topological spaces equipped with addition, a commutative and associative addition. So you could ask me, what is the commutative and associative addition? Well, the level of flow modules, it's obvious. It is disjoint union. Addition. If I tell you, if I have an assignment, to every critical point, I assign a manifold in corners, and another assignment, to every critical point, I assign a manifold in corners, I can just take the disjoint union, and this equation here will still hold. This is now disjoint union of n0 and 1. This is a disjoint union of n0 and 1. Of course, this not still satisfies the diagram. Okay, and if you are normal human being, it is obvious to you that disjoint union is associative and commutative. You put them here, and then if you put the other one next to it, that's associative. And if you put them here and you do that, then that's the same thing. Well, unfortunately, that's not true. So all the trouble arises because in set theory, x times y times z is not equal to x times y times z. And this is actually not so bad, you can deal with it. X times y is certainly not equal to y times z. They're not equal. I mean, yes.
Why are you talking products? You were talking about disjoint unions.
Thank you. Thank you.
That
Same
one's
thing.
harder.
Thank you.
And now that's false. These are equal in some theory.
And they're still not equal in set.
Okay.
This joint union will involve some parentheses, and the way you put the parentheses, anyway, they're not
This is
equal.
formal disjoint union. I think actual disjoint union of sets.
Yeah, but what exactly? This joint union has to be taken somewhere. Okay, we'll fight with this later.
So I think you should write down a bijection.
Yeah. You have to actually write down some matter. So anyway, so all this trouble is in making sure that these things are actually associative and commutative. And that somehow there's a whole machinery that was built by homotopy theorists just to deal with this, but the intuition is exactly what I said, that you're just taking this. So that's that, and then the last thing that I wanted to say is, how about the other perspective, where you think of it as a homology theory? So for the homology, or to extract the homology theory. Well, what you do is so now we have our manifold M, or rather, we have our flow category, okay? M bar, and we now give ourselves a topological space. So given a topological space X and a flow category M bar, okay? We want some invariant of X, okay? Well, for the two of them, because it should depend, because this could be a homology. So we just look at flow modules over X. So I have this IE for every object. Unfortunately, I'm using the same language, use P here, P of M bar. We consider that we are given something which is called N of P, and I switch my notation so that that's less confusing. Okay, but now this is a manifold with corners still, but with a map to X. And then you have this equation, and this should be over X. I'll write it, and that'll be the last thing I do. And we have and E from M bar Q to M from Q, okay? This should be associative. Oh my goodness, it's the other way. Okay, this is associative, just like before, but this has a projection to X. And this has a projection, of course, to M of Q, and then for the projection to X, you would like for the module maps, or how this acts on this, to be compatible with the projection. That gives you a bordism group, that will be an invariant to X, and then you can check that that's homotopy invariant, and that it satisfies the Meyerbeer-Torres property. Okay, so again, the goal is to not explain what a spectrum is, but this is the geometry that goes into it. And to produce a spectrum, all you have to do is do everything I said, just a little bit more carefully. And I think that's okay. Okay, thank you very much.
So I say,
Go ahead.
so I saying the bordism group is actually the homotopy group of the infinity category. I don't know if it's the correct word.
Yeah,
Flow modules.
yes.
I see. So there is sort of like a stability inside this category.
Yeah, I didn't say that, but of course that's not. It turns out this category is stable, but you don't need. Well, whatever. Yes.
You just need to take a homotopy group, but.
The question is, how do you take homotopy groups? That takes some annoyance. As it turns out that you can do it in an easy way because you have this, because it's con. Okay. Yes.
The classification of CQFTs, when you have a bordism theory of symmetric harmonic functor, you end up getting an algebraic structure associated with bordism theory by product and combination of bordism. But this.
Yeah. Yeah, so here, I mean, that's exactly what Simon called. I somehow have been thinking, the next step is to realize that products of manifolds, in fact, makes this not just into a spectrum, but into a ring spectrum. Right? Where they come from, products and manifolds, and relationship between products and discontinuity. But to formalize it, again, you need even heavier machines than what's required to do that. Yes.
Can you draw a picture that explains why there exist spectra that are not E infinity but are E2?
Yes, but that's not for right now. Yes. I mean, the answer, as you probably know.
Boss-Sullivan picture.
No, not Best-Sullivan picture. It actually comes down to thinking about when you do framings, if you try to do two periodic framings. You know, it's complicated because usually you see, here I wrote some stuff saying you can put some stuff everywhere, okay? And if you look at just bare manifolds, you never see any of these issues. Everything looks perfect. And it's always in the structure that the difficulty arises in ensuring that, you know, multiplication and various operations are compatible with it. Maybe the only thing that I will say is, what does it mean to be stably framed? It means that you have a trivial vector space that you've identified everything with, okay? And already, when you try to take products, you know, you have Rm times Rm, and you're supposed to identify this with Rm times Rn, but that matrix is non-trivial, and that's where most of the difficulties arise, come from. Now, it turns out with the sphere spectrum frame bordism, they're okay. You don't run into this issue. But if you try to do something slightly more complicated, like two periodic frame bordism, then it's a real problem, and then it's not strictly case. But I cannot say more. Yes.
You at some point you mentioned that your construction was inspired by Witten's construction in some way, and Witten's construction uses this heat kernel flow, which moves differential forms to basically delta currents of the stable manifolds.
Yeah.
Why?
Yeah. So it has to do with this step where I say make it transverse to the gradient flow, and the picture that I have in mind is that I take my M and it has a Morse function, and then I have some other manifold N mapping to it, and then I flow for the map for a very, very, very long time. So here's my M. Morse function. Here's the other N. It's mapping here, okay? And now you imagine that you take this function phi and you compose it with the flow of the gradient flow. And what that's going to make, what's going to happen is, you know, everything, if we have a critical point here, there's going to be some fiber. Okay, and then everything below it for a very, very long time will just be completely trivial. Loss W unstable. Okay. And all the interesting topology of this map of the N to will be concentrated at the critical points below. But what we should really expect to happen is that all the complicated topology that takes place in codimension K will get caught up in the critical points of index K. So there will be some kind of decomposition of this bordism class into pieces, each of which is supported in a single degree. And that's actually how we prove that this flow module, this bordism of flow modules agrees with bordism with the bordism of N, because we say, oh, well, you can just filter. And on the associated graded, this is just one critical point. So you just expect to have a copy of the bordism of a point, okay? And then you just need to check that, you know, there is a map between them compatible with the filtration on the associated graded induced isomorphism, and essentially you're done. Okay, so somewhere hiding in the proof of isomorphism is this thing of it. Okay. Yes.
Yeah. So starting with the flow factory, which I imagine would not be automatically stable. And in the end, you come up with the space of flow modules, and you say this is gonna give you a spectrum where like they go within the category, whatever.
Yes,
Just the like stabilization taking place when you were doing the bordism theory of the stable.
yeah, I mean, it's a little bit like saying, you start with an algebra and you look at a category of modules, and the category of modules has cones, and then it's stable. So it is exactly actually what's happening. The equation for M is exactly like an equation for algebra. I mean, the equation, like M times M maps to M. Right, and just ignore all the object. This is what it looks like. This is an algebra. So it's exactly the same phenomenon. You have an algebra, you look at modules, category of modules over an algebra is stable because there's cones.
One more question?
Yeah, maybe like I'm wondering like because you require the manifold to be the map which transfers to all the critical points, and that will give you like just a sub collection of all the maps.
Yeah, that's generic.
And why? Oh, that's generic.
Yeah. Yeah.
So that's why you can recover all the.
Yeah.
More questions? Okay. Go out. And come back at 10:30. Yeah, fix it, fix your time.